This method can help answer key questions in the environmental and ecotoxicological fields about the relationship between cardiac and locomotor activities under various acute and prolonged stressful conditions. The main advantages of this technique are that crayfish don't require complex prior manipulations or prolonged adaptation and are capable of bearing sensors for a few months between moultings.
The implications of this technique extend toward ethological, physiological, ecotoxicological, and industrial applications, as crayfish-aided non-invasive biomonitoring can be implemented in laboratories and water treatment and supply facilities.
Though this method can provide insight into crayfish cardiac physiology and behavior and water quality control, it can potentially be applied to other large freshwater and marine crustaceans.
Visual demonstration of this method is critical for understanding the link between non-invasive sensor using near-infrared light for hemolymph evaluation in crayfish heart and movement detection modules based on image processing.
A few days before beginning the procedure, select adult specimens with a carapace size of at least 30 millimeters and examine each specimen for the absence of disease and whether they lift both chelae when touched. Then, allow the healthy crayfish to acclimate in a tank of settled tap water until the day of the procedure. As soon as the sensors have been prepared, open the sensor software on the computer and enter the number of crayfish to be fixed to the sensors and displayed on the screen. Set the number of crayfish heart rates to be visualized and use a paper towel to dry the dorsal carapace of the first animal. Wrap the chelae and abdomen of the crayfish in the paper towel to avoid damage and to eliminate additional stress to the animal. And attach the sensor to the dorsal carapace in a position that facilitates a maximal cardiac signal amplitude. Holding the crayfish with the sensor in one hand, use the other hand to add a drop of freshly mixed epoxy glue onto each of the 4 auxiliary wires located on the sensor. Then allow the glue to dry without moving the sensor for at least 5 minutes. When the glue is no longer sticky to the touch, place the unwrapped crayfish and sensor into a box without water for a few more minutes until the glue is completely dry. Before moving the crayfish back into the tank, immerse the cephalothorax into the tank water for a few seconds, several times, to discharge the air that is accumulated in the gills, and leave the crayfish in the holding water tank for approximately 1 hour to remove any excess chemicals. Then, release the crayfish into the experimental water tanks for 1 to 2 weeks of acclimation and under the appropriate experimental conditions, depending on the observed physiological indices. As soon as the crayfish are placed in the experimental tanks, start the software. The video camera will automatically switch on. Then select the movement detection option and locate each tank on the screen to start tracking the behavior and linking the behavior of the crayfish with the cardiac activity recordings. The recorded crayfish cardiac and behavioral activities can be saved in a TXT format file. It is crucial to include the locomotion of the crayfish in the analysis, as this activity can cause changes in the heart rate. For example, in this experiment, 10 seconds after the start of the experiment, a food odor was delivered into the tank via a peristaltic pump. At 14 seconds, the crayfish recognized the stimulus and its heart rate slightly decreased due to the so-called orienting response. After 20 seconds, the heart rate increased, resulting in a decrease in cardiac intervals. At 26 seconds, the crayfish moved toward the stimulus source, and both the physiological excitation caused by the food odor and the locomotion initiation resulted in a substantial heart rate increase. At 37 seconds, there was evidence of abrupt crayfish motion that could have substantially contributed to the heart rate growth during the reactions to the stimulus. Indeed, a disturbed crayfish typically demonstrates an increase in heart rate that is often associated with occasional locomotion. However, even motionless crayfish can demonstrate a high heart rate that also indicates a pronounced stress. The heart rate of an undisturbed crayfish is characterized by a monotonic amplitude of the heartbeat curve and by approximately equal cardiac intervals between each cardiac peak.
While attempting this procedure, it's important to remember that a quick and thorough sensor attachment will cause less stress to the experimental animals, enabling the acquisition of precise physiological characteristics.
More advanced monitoring methods include the use of fully contactless crayfish monitoring, which allows the heartbeat frequency to be determined using only the combination of a near-infrared sensor and a sensitive camera.
After its development, this approach paved the way for researchers in the fields of behavior, physiology, reproduction, and ontogeny of unrestricted crayfish and other large aquatic invertebrates to explore environmental and anthropogenic impacts on bioindicator organisms.
Further, non-invasive biomonitoring has a very practical application at the local brewery in the Czech Republic as a real-time water quality early warning system, where the stability of the water state is continuously assessed through the dynamics of crayfish ethophysiological characteristics.